that.
Okay. Hi everyone. I'm Naga. So this is like our third week of system design discussions in ST skills. So today I'm here to present like some topics which I learned from designing data intensive systems book. Chapter 3. It's on storage and retrieval. And the topic which we'll be discussing today is like the data structures that power your database, like or like another way, the storage engines which run behind your databases. So I hope you can see the topics I just briefly listed out there. So we'll talk about log versus page oriented storage engines and what they mean, and briefly like some of the three categories like hash indexes, SSTables, and LSM trees, and B trees. These storage engines are already used by many databases already, and yeah, we will discuss about that. And again, like I encourage you to after the session go ahead and read the book, or um, you do your own exploration to understand clearly or to cross check things. So I'm here to just present from my version of the learning. Okay. So let's get started. Like in general, when we talk about a database, what comes to mind? So the concept of database is that like if we give some data to the database, it just stores, and later when we ask for it, it just gives what it actually stored. So that's a primary purpose of our database, right? Like whenever we give something, it has to store, and whenever we ask something that it stored, it should give us back. So in a simplest form, the database can even be a simple file in a database, or like in a file system. If this is a file system, like magnetic disk or something of multiple layers, like, and if we have one small file here as a small block of file, and if we store something here, and whenever we ask, we can just retrieve from that file, and we can return the data. So even a file can act as a database. So before we go ahead and understand like what is log structure versus page, so, or like maybe we'll briefly talk about that log structured and page oriented. So the storage engine term, it means that like it is the engine behind your database which maintains the storage and retrieval part. Like the databases, even if you talk about like whether MySQL or whatever the database that you talk about, it internally uses some storage engines like InnoDB or XAMPP. There are so many types of storage engines. There are like log structured storage engines like RockDB and all, which are all level DB. So these are all the storage engine names. So depending on the storage engine that database chooses, the idea, the structure of the data, the way it stores the data on the file system or on the cache, I mean, like it will be different. So it's important that like we understand the storage engines, and in order to be able to make better decisions, like whenever we are making a design decisions. So the log structured storage engines, they follow the concept of log. So the term log, which I'm talking about here, is like an append only sequence of records. Like you just you treat this like as a log, and this is if you are adding some data, you just add like append only. So this is like 1, 2. If you're adding 0, 1, 2, 3, 4, you keep adding. You don't delete anything. So it's like an append only type of transactions. If you have a scenario where you are not modifying the data frequently, but you are only adding the data to your database, and and probably like there could be same data which gets appended again and again, but you can merge them later. That kind of storage engines are called log structured storage engines, whereas like the page oriented storage engines are nothing but it organizes the data in the form of blocks inside the disk, if this is a disk. And there are some small blocks of our sectors in disk, and each sector is divided into small blocks of like 512 MB or KB, 512 KB. And inside this block, there will be set of files that we actually store, right, like sequentially. So if the storage engines works on the disks in the form of these blocks and pages, so the page, I mean, like that's why they will be called like page oriented. The example of this is B trees. The example of log structured are like this LSM trees or like or SSTables. Any questions so far?
What is LSM?
LSM is log structured merge tree. The full form is like log structured merge. I'll actually get to that. It's log structured merge tree, and I'll tell you like how the name came. And the SS tables means sorted string tables. I'll get to those in detail. So first, I just wanted to give an overview of what log versus page structured storage engines mean.
So Naga, this storage engine will only take care of partitioning the memory, so that to acquire the memory for page or either for the log.
No, I mean like it's basically depending on which storage engine the database chooses. It takes care of everything, like the way data is stored, and that's kind of the core engine which stores and retrieves the data for a database whenever some requests came. Like
Okay. Means from the disk, it will take care of allocating the memory for a particular page.
I mean, like for
No.
allocating a memory, it definitely needs to rely on operating system. But when we talk about page oriented, it means to store the data in terms of pages or the blocks that the disk is normally used to. Like at the end of the day, we need to store data on disk, right? So the page oriented storage engines already concentrate on that, like storing how to efficiently store the data on disk. So that's what.
And there is, if I can just add one thing there. So when we talk about storage, right? Just to draw an analogy, you can think of it as a data structure, right? Just as a simple data structure, arrays or linked list, whatever we discuss. So the storage, whatever Naga is talking about, this is also similar concept, right? What is that data structure that you use to store your data? And coming back to your point about disk and how memory is allocated, memory allocation, reading from disk and bringing the page to memory or the data to memory is a whole different like area. But I think what Naga is focusing on is more about storing data in first place, and it can be I think what you are focusing right now is probably disk, but it can be there are in memory databases, right? So they are in memory databases, they are disk based, so there is a whole gamut of structures, but the high level idea is that you want to focus on what data structure you're using.
Okay, sure. Thanks.
Yes.
Sure.
So yeah, as I said, like this, all these data structures like the hash indexes or SS tables, B trees, all of this are like the storage engines itself, because they are again the data structures and which power those storage engines and in turn the databases. So if there are no questions, I'll get to like discussing like how the hash indexes work. Okay.
Naga, there was one point that I thought might be interesting to share, like about advantage and disadvantage of one versus other. So, for example, I remember about log, but not so much about page. Like for log-based structure, right? The way we are talking about appending. So, its advantage I see is it's like simplicity, right? You're just adding to the end. But the downside is like you have to manage the space. Like if you keep adding, you need some way of space management because it will keep growing. So there are compaction techniques and all that that comes in.
Yes. Yeah, so we will actually compare like after we discuss all this.
Oh, okay. Sorry to jump in then.
Yeah, no problem. So I wanted to go like this in depth, and then we compare like how this gets compared. So internally, when we compare LSM and B trees, they're like block structure versus the page oriented. So we'll look at the advantages and disadvantages.
Okay.
Which DBMS use the log structured way?
There is a RocksDB, which is used by Facebook and LinkedIn and many others. And there is a LevelDB. It's also used by Google, Bigtable internally. And Cassandra also has a flexibility to choose log structured, like LevelDB, I think. And there is a React NoSQLDB, which uses hash indexes. So I'll actually, whenever I talk about this, I'll also mention.
So one more follow-up question. So like any NoSQL or SQL database, they can use either of the page-oriented or the log structure, right?
Yeah, I mean but I can say most SQL databases rely on page-oriented, but there are few SQL databases which also use log structure, but I think it's minimal. But the other way is more, I think. Most of the, I mean, like some of the NoSQL databases use both, again, B trees as well as, yeah, there are both examples. Yeah, you can technically use both, like you have to ensure that properties, right, ACID properties are if you are doing a SQL database.
Yeah, and I think it also, there would be a point about scalability, like your choice of choosing, like, or when you look at the commercial databases, the reason they're using one versus other is tied to what Naga said about ACID transactions and also the scalability aspect, right? How like the key value stores or log structure in general, they seem to be the kind of flexibilities they offer are different from relational. So.
Okay. So with that, I'll actually get on to this first topic, hash indexes. So before getting into this, like I'll take an example of like, let's take one example of a file. And say you want to convert a file to a database. So, and if you are taking example, like we are storing the key value pair data. So what is the simplest form that we can actually do if we think of if the data is like block structured, like append only? So one of the scenario we can actually store, if this is a file, is like you can actually store key1 and comma some data, some record data, and then you can actually store like key2, and then actually you can store another record, and then key3, and then you can store another record. So since this is an append only, you can continue to append to the file, and then like whenever somebody asks, give me the data for key2, then you just go to this file and just check where the key2 is and get that data and return back. So that's one of the typical algorithms without thinking of any data structures. This is in a simplest form. Like you can have up to key n, but the only thing is that the issue with this approach is like you have to go and scan all the entries and find where that key is, and then return the data, whichever is latest of that key. So your complexity, like if you think of time complexity, it will be like linear.
So if the key 3 appears like multiple times, the last copy of the key 3 would be returned, right?
Yeah, correct. So if this key 3 was somewhere here, so this is our latest data, right? Because this is an append only in log structure. That is what we wanted to return. So since we'll be scanning all this, like we will, we just need to return the latest entry. So one of the way we can improve this kind of storage is like, how about if we use a hash table to store some pointers to each record. So in this scenario, maybe we can just say that like we'll have an in-memory hash table. Like whenever we say hash table, it's definitely has to be like in memory. So let's treat this like as a RAM and this as a disk. So in a RAM, like I'll have the key 1, and then we can just insert a pointer to where the key 1 record is stored. And we can also store key 2. And we can just have a pointer to key 2. So and so on, like for all keys in the file. Not that this record I just gave, like I'm ending in the same line, but technically can end up in any lines. It can go as much as the contents exist. All we are actually storing here is the offset in disk where this is actually stored. So basically the location in disk, it contains like which disk segment or like which sector, and then what is the offset, etc. All those details maybe we can just store in a hash map value which points to that. Whenever you want to look in the value, you just find the key in your in-memory hash table, and you directly get to that, and you can read sequentially until before the next key starts. Like, so you can have a marker pointing to. So let's say if you use a CSV, so we can have a end line signifying that this is the end of the record. We can read until to that end of the line what that record actually contains. So this is a concept of hash indexes.
So Naga, if there is a key like which is repeated, right, like key 3, and the last one is the most recent one. So in that case, hash map will contain entry for key 3, and will it point to the last one, the most recent one, or
Yes.
the right?
Yeah,
Okay.
most recent one. Yeah.
Okay.
Because it knows that it has. Yeah, this is the recent, so it will only point to the latest one. So I didn't actually write key 3 here. And I mean, like if I mean, like for deletion and all, those are like special cases. We'll take like we can think of how we'll handle a little later. But this is the high-level idea of hash indexes. Like the only requirement for this hash indexes is that all your keys, like your key size. I mean, like if you have like 1 billion keys, and those keys are small in size, and if you can fit all those keys into your memory, that's the only requirement. So all the keys must fit in memory, must fit in RAM. If your data cannot fit inside a RAM, I mean like not all the data, only the keys. If the keys are large enough that it can't be fit into the RAM, then you cannot use hash indexes. The data can be as big as possible, but the keys needs to fit in RAM. So that's the idea of this hash indexes, and this is used in React database. When I say React, it can use 2 types of storage engines. So the storage engine which uses this hash indexes is Bitcask. You can actually find more information on that. So Bitcask is a storage engine which uses this hash indexes data structure. And Yak also uses another one, which is log structure. We'll get to that later. So far, any questions on this? I'll actually get to what is a problem that we could actually come up. So let's say that you are actually writing to a file, and this file keeps growing in size, right? So yeah, one of the scenario that we have to do is like, let's say if this file size increased to like some limit that we wanted to monitor, like 100 MB. So whenever it reaches this mark, we can just say that we will take this file and actually store separately into the disk and create a new file, a log as append only. So we'll just start storing. I mean, like we'll move this to say this storage to already like permanent storage. I mean, like it's already permanent storage, but this will be this piece will be kept aside, and we will open a new one, a new file like file2, which is current, and we will also erase all our keys here. And start like if we are adding a new record, the key 10 will come here and all the data for key 10, and the key 11 will come here, so all the data for key 11, and then you again make it key 3 here, so and again you make it key 2. So you adding to the new segment. So let's call this as the segment which is already committed, and this is the current segment.
Hashmap will have access to all segments.
No, only the current segment. The hash map, the hash table, the hash index which is in memory, the hash table which is in memory, it only has access to the current segment, not to the old ones.
So if in my hash table I have key 2, which I move to other segment, now the current segment will not have the key 2, right?
Yes. Yeah. So yeah, how it actually works around, yeah, I mean, like I'll come to this read part. So the way it works, like when I look into the hash map and I find something is not there in the current segment, I actually go back and see which is my previous segment.
Okay.
So this is like the previous segment. Like if we go in descending order, if the current segment was like 5, I'll go back to the segment 4 first.
Okay.
Whether it is there or not. If it is not there, then I'll go back to another segment, segment 3. I'll check. So it keeps on going until to segment 1. So now you would have, now you can easily guess that this is a read index, right? So for the read, you have to keep looking all the segments, find where you have this key. So, but you know that. So yeah. One thing.
And then bring it to current segment or leave it there only?
I'll actually come about like how we get rid of these segments.
Okay.
So,
okay.
Yeah. Yeah. So since we are talking about key value pair data, we know that if the recent segment, like if the current segments contain key 2, then I don't need to look into any of the previous segments.
Right.
Because the latest value is already here.
Right.
So this worst case will happen only if the key is not present in any of the segments.
Okay, not any segment. Okay.
Yeah. So if the key is already present in this segment, it means that I already have the latest data in the current segment. I will just return quickly. So it is faster.
Suppose,
yeah, only if the key is not present, then it keeps going to the previous segments.
Let's
Okay.
say I want to update key 3, right?
Mhm.
And let's say key 3 is not in the current segment. And
Okay.
let's say, update, did not update all the, they all only update a single value.
Mhm.
So how does it,
Yeah, updating a single value means like you are appending only. Since there is an append only database like log structure, we are appending to the current segment. If you are adding a new value to the key 3, suppose if key 3 was here with some value 3, and here I'm appending, like if you want to update that value, I'll just say that key 3 and value, new value 5.
but I mean like in the SQL table, right? There's we have a key and we have multiple value like, address, name, and now they only update the address. They don't give a name. Then, how we gonna get the name from the previous segment and put it into current segment?
I don't know, like if you are updating the value for a key, so since there is no update concept here in the log structure database, all you do is append only. I'll talk about like how this segments are actually merged. So as and when the writes are happening, this keeps writing to the current segment. If the current segment gets full, it's on a certain storage limit that we normally set the limit for, we can just roll over to the keep this segment aside and create a new segment and keep appending to that. So this hash tables also, I'll talk about like how we dump this for a quicker restore. So since you get the segments like one after the other piled over, if the writes are happening, so the process that we do in the background is like we merge these segments. We know that this all the segments can actually have a similar set of data, right? So let's say this has key 1 and this also has key 1 and value 3 and value 2. And then let's take another example, key, I don't know if I'm correct, key 3. I mean like if it's visible or not, sorry. So if key 3 has a value of 4 and here value 5, and you have some keys which are not present here or here. Let's say it is like key 5 and this is key 7, and this is a latest segment like segment 4, and let's take this as segment 3. So when you are merging these two, how it works is, let me adjust this. When you are merging these two, so I have the key 1 here, and this is the latest segment. So I just ignore this value in the previous segment. I just take this into a new segment. So I just take this key 1, whichever value that I have in this segment, segment 4, that's what I'm going to take here in the merged one.
It will keep on appending segment. So it will background process keep on taking the latest value from each segment and maintaining a previous segment.
Yes, correct. So you just worry about only the latest values. Yeah, you just worry about only the latest value and keep discarding the old ones. Okay. And over the period, like if this was like 100 MB and this is 100 MB, and the merged one might be like 150 MB, depending on how much overlap they have. And if all of the keys overlap, this will be just 100 MB. So it's 150, assuming that only 50% of the keys overlap, or like some of them are new. So this merge will keep on happening, and you know that the maximum limit of the keys is what you could actually fit in memory. So like a single hash table could handle. So this segment size will not grow very large, even in the disk.
Naga, I have a question here. How we will get to know which segment is having the latest key value?
The current segment that you are always writing to should have the latest value. If not, you go back to the previous segment. So you maintain the order, right? Like which segments are there. So since this process keeps happening in the background, the idea is that you should not have so many segments to look for.
So it will traverse from the latest segment to the previous segment and keep on doing backtrack until it will find a latest key, or whatever is the first key it will found. So we will consider that as the latest.
Okay. That will be the latest one. Correct.
And why it merging the current segment? Would it also lock the current segment so that there's no update on the current segment?
The current segment is what we use in memory. Like if somebody is current writing, like you have like database writes happening, right? The writes always come to the current segment. So rolled over segments like which you already done writing, like at certain size, you keep them separate. So those are the segments where you will have a background thread, which will actually continue merging this. And I mean, like this merging also results in compaction. That's why it's also called as compaction. So this previous segments will keep compacting. So we'll just let's say by the time we get this segment 4, 3 and 2 and 1 would have merged into one. Let's say as a new segment. And now that you have only 2 segments to merge, like segment 4 and segment 2, or whatever this merged segment. So we just keep on working on merging whichever whenever the segments get available, the background thread will keep actually looking through this, and it will be like find the key. If it exists in the previous, you just ignore. So you take whatever is there in the latest one.
Naga, one question here. Like, let's say there are 100 segment which is already filled. Now I'm working on the 101 segment. So is there any flag to tell like I have already taken care of 100 segments? When you are doing this like contraction again, you need to start from 101. Means you don't need to see the last 100 segments also.
Yeah. So if you have a value in latest segment, you don't need to care about all other segments because you already have the latest value. But the idea is that we will not have 100 segments in the real time, because the fact that we have the segments piling up, it means that our background thread is not running. The thread which runs merging and compaction, it has to make sure that the number of segments in the file system are minimal, because otherwise your reads will keep on taking ever. I mean, like they'll take like forever if the key is not present.
Okay, means in that background thread is also like primary and secondary, because there should be some failover mechanism for that thread also.
Yes, obviously, yeah. So it's important that in this process, like it's important that we keep merging these threads in the background, and if we have a latest key in one of the latest ones, it will ignore in all the previous segments. It just takes the values in whatever the latest segment that is merging.
Okay, sure, thanks.
So now, if there are no more questions, I'll get to that. What if the key is not present in any of the segments? Then how can we improve the performance for that scenario? So we talked about that example, right? Like if the key is not present, the worst case is that it ends up in it keeps reading all the segments all the way back. And if you have some number of segments, then it has to go and scan all the segments completely to figure out that key actually is not present. So the read would definitely take a lot of time, right? So how can we improve the performance for those scenarios?
Use Bloom filter.
Yeah, correct. So good point. So the Bloom filter, as we know, is a data structure, is a approximate data structure, which uses a simple bit array map of some size, and it uses some hash functions, and it's effectively, all you need to know is that it effectively can tell if something is not there in the setup. So, but it cannot tell if something is present in the set. It may tell that it may be present or may not be present. So, but we know that it can definitely eliminate false negatives. So this false negative is that the record is not present in our database. So in that case, like we can use a Bloom filter to have a hash values of all the keys that we store in this database, that is, which will normally fit in the RAM. So we'll have a the Bloom filter of all the maximum key size, and we'll use some set of hash functions which will always map to a certain value. So for each of those keys, and if we find, like if we want to read some data, we just make sure that the Bloom filter says that if it says that there is a false negative, then we don't look in and say that key not found. And if it says that it is there, then like we will continue looking in all the segments. In the worst case, we may find that it may not be there. So, but we are eliminating most of the false negatives through Bloom filters. Only few scenarios we might end up doing the scanning. So the cask actually uses the Bloom filters to filter these scenarios. Any questions on this?
So I think Bloom filter is itself its own concept, but
yeah, I don't. Yeah, that's why I didn't want to cover that in detail. I hope one of the sessions Roger covered, I think.
Yeah, just high level, like Naga mentioned, that Bloom filter could not guarantee that things are there, but it is good in telling things are not there.
Mm-hmm. It's a probabilistic data structure, one of the probabilistic data structure. There are many other probabilistic data structures like count, min, sketch, and few others, which also rely on and also used for some other top K related elements. But like that can be its own topic, and I hope like some people can actually take this if they want to learn. They're really very good to learn. So
yeah, yes, Naga.
And one of the other scenario that I wanted to cover is like this is for the ones in the read path, right? Like what if you want to delete something? Since this is an append only, so how the deletes are handled in this bit cask or like the storage engine or this data structure. So one of the ways it does is like say in this we want to delete the key 11. I will just append at the end and say that key 11 mark it deleted. Some delete flag I'll keep at the end. So when some background thread is actually looking into this, or like when we are actually finding this, if we find a key 11 as a delete marker, it just ignores that entry from during the compaction. It just ignores whichever the delete flags are there. It will just ignore from merging if it figures out a delete flag. So those delete flags or markers are also called as tombstones. So that's how the bitcask actually does. It just has a marker in the append only fashion, but whenever it's scanning and if it finds this flag, then it actually ignores that entry. And the other scenario, what could happen, like what if let's say like if you want to restore some of the segments into memory and for faster lookup. And the best way the bit task does is like whenever this the current segment and the current hash table, like it actually, whenever they are actually writing, and when it actually moves to disk, the permanent storage, it also stores a snapshot of this hash table in memory. And when it's merging the segments, it also makes sure that it merges the hash table concept. Even if not, like we can actually quickly build this hash table if we want. But since that is time consuming, normally this snapshot is stored in disk somewhere to so that if you want to read something in segment 4, it quickly loads that segments 4 hash map into into RAM, and then quickly looks up using that hash table. So we just need to make sure that whatever the key and offset value or dump of hash table that we have, we also store that snapshot when we store the segments aside, so that like if we want to read something from that segment 4, like we load the hash table used for that segment 4 into in memory, and then so that the lookups can be faster in that segment.
Okay.
And that is one thing. And it could also happen that if you are writing something into the current segment, there is a chance that the server can go down.
Oh, yeah.
So in that case, like one of the ways I think this will be improved is they can maintain a write-ahead log before writing to this segment. Just like the all databases maintain. But in the worst case, even if we don't have that, we just need to go through all the entries in the segment file and then rebuild this hash table.
Yeah.
It's the each record, the space, I mean the disk space for each record, wouldn't that, I mean, does it have to be the same for the number of byte or the disk space for each record? Do they have to be the same or they can be different?
No, they can be different. Yeah, I just gave for example, but the key, one of the key can store like 1 KB of data. The other key can store 2 KB of data. So it's not uniform. So each of the values can be different. And since we will have a end line marker, right? Like new line marker. We will just like, if it stores like in a CSV format, we'll have this new line marker marking the end of the entry. And the other key 11 offset will actually begin on the next byte. So I don't know if I can quickly represent that. If we represent a byte array, yeah, let's say this first record key 1 and then colon this, it can go on until here. And then say, let's say you have this new line, and then this, let's say this is 51 byte number or offset, so called, and this is the 0. So one of the key 1 will point to 0, and the key 2, since it's starting here, it points to this 51. If that was a byte number.
Thank you.
So I mean, like since it's just a sequential and in the form of a file, so we just keep appending till how long the value takes space.
At any given point, is there only one hash map in memory?
Yes, and if maybe in the read parts, like if we want to read data from other segments also, then we keep loading the segments hash table also into memory.
Okay.
Any other questions? I'll just make sure that I covered all of them. Just a minute. So, and one thing I just forgot to mention is like if like since the writing is always happening in append only fashion, we don't need like multiple threads taking care of the concurrency. So all you need is like a single writer thread which keeps writing to this file. So most of this is actually taken care of using a single writer thread. But since it's append only fashion, and the disks are also very fast in the, if you are writing the data in a sequential manner, the disk speed is higher in this log structured kind of, if you write sequentially the data. So it is how the log structure works. So in general, like this React actually, the bitcask actually works efficient in writes, but for reads, it's not quite efficient like our database or how the other RDBMS works, like using bigtrees. So we'll look into how they also work, but these are in general fast for writes.
When there's only one single thread to write, but like with multiple multiple record come at the same time. So how does that single thread handle?
It's just like a queuing up, right? Like if the idea is like the single thread, if it's working, like it keeps. Like even if you have multiple threads, all you need to make sure is that where you have the data. But like I'm saying, like single thread is enough. But like if you are taking care of multiple threads, in that case, only thing is that the thread always needs to make sure that it looks in the end, or like there is a chance of corruption if both threads think that this is the place where they want to write a new record, they might attempt to write into the same. So I think that's the reason maybe it's using single thread.
Is there a queue in front of the single thread so that
yeah, I think definitely it has to, it needs to have some form of internal queue or write ahead log in front of it, because that write ahead log can actually, so suppose that this is the actual file, this thread can actually, what it can do before this, like all the writes we can write into one of the write ahead log. We can keep appending. It is again the similar format, but this thread can take and keep appending the records. So we can try to do in that way also. But I think the main idea of using single thread is that since it's using, like single threads are still efficient when it's writing only to the concurrent, right? Because the disk is also writing pretty faster. So maybe something you can explore on more, like how this thing works. But I learned that like normal implementation choice is to have only one thread. Like like if you have the multiple threads, you always running into that race scenario, right? So which thread will get the lock, and you always have that overhead of maintaining who gets the lock on this, like, and then only the thread will actually write. So even in that scenario, like since you're writing only to the one file, the resource is one. If you're writing to multiple files in parallel, then that may be another scenario where you can use multiple threads. But since the file resource is same and you're appending just to the end, I don't see any value in adding another thread to write to the same, because the lock can be only with one thread. again, like I'm not expert in concurrency, but like you can actually try look up something on that.
Okay. Yeah.
So before wrapping up this, I just wanted to mention one of the disadvantages that we can think in hash indexes is that since the keys are not like arranged properly, like they're all you just keep on appending, right? You don't maintain any order. So if you want to do a range query, like give me all the key 1 to key 10 records, then you keep looking all those records in across all the segments that you have available to be able to fulfill, because some can be in the current segment, some can be in other segment, some can be in other segment. If you have to fulfill that query, you have to keep looking across all the segments to be able to fulfill. So that's one of the disadvantage here. So we won't be able to do the range queries efficiently in this. And one another important thing to remember is that all keys should fit in memory, because to be able to read the data efficiently from all segments, you should have a the space enough in your RAM to load all keys in memory to be able to read efficiently. And yeah, that's all about hash indexes. And maybe we can get on to the next topic, SSTables and LSM trees. If there is any quick question, please let me know. Okay, so no questions. So I'll continue to this SSTables. SSTables stand for sorted string tables. So as a name suggests, like you'll have a clue that this log structured engine or like data structure will actually store the entries in arranged order. So the main thing is it stores the keys in arranged order, or like whatever sorted order. So on quick question, so what are the data structures that come to your mind when we talk about sorted data, which can keep efficiently or store efficiently? What are the data structures that store the keys in sorted order?
Tree sets like binary search tree or something like that.
Yes.
Variety queues?
What is the other one?
Heaps.
Heaps. Okay. Heaps doesn't keep always in sorted order. It just returns whether min or max in log n time. But like they won't keep all the data in sorted order like BSTs. But what is the problem with BSTs? Like
every time you do insert or something, you have to so if it is a balanced binary search tree, it is good. Otherwise, it would be tricky.
Yeah, so since like BSTs cannot be balanced, like the lookup time can become worse to O of n in the worst case if they are not properly constructed. So what are the self-balanced binary trees?
AVL tree or red black trees.
Yeah.
Yes. So the red black tree
AVL tree
or AVL tree. Yeah, these are some of the two famous, which I don't know. I think there are a few other variations also. But like these are good in storing the keys in sorted order, and they are balanced also. So we always get a lookup of log n. So the idea of SSTables is that like what if we can maintain what if we can use a self-balanced BSTs or red black trees to store all the keys in sorted order. So that's the idea of sorted string table. So what they actually do is, let me come to that. So let's take this is the RAM, and this as a disk. Sorry, normally the disks are represented in round. I don't know how to represent it. So the idea of this SSTables, as we know, like this, if let's take an example, we are using red black tree. So if we are having this red black tree here in memory, which is actually taking, like, let's take the scenario of like 30 here and 20, and then like 50, and this is having, let's say, 40 or 60, and then 10, 25. So this kind of, if these are the keys, this red black key, which is in memory, can actually store all this key value, I mean, like sorted by these keys. If at all, if you want to find a range of this, give me all the keys from 10 to 30. Then we know that, like, from 10, if I'm moving in ascending order, I just return all this, like if I traverse in order 10, 20, 25, 30. So I can quickly return the subset of entries if I'm querying for some data in this structure, right? So the idea of SSTables is that, like, whenever writes are happening, you will always keep this in-memory table. So this in-memory table is nothing but our red black tree or any self-balancing binary tree. It is also called as mem table. This terms of mem table and SSTables was I think introduced by Google in one of their big table research paper, and that's how this mem tables and SSTable name came. And so we always have this mem table in memory, and whenever it hits certain size, like 50 MB or whatever, like 100 MB in the previous case, what we can actually do is we can dump this to disk. Dump this tree to disk, like as one segment. So all this data of red black tree this mem table will be flushed to disk whenever it hits a certain size, and we will initialize a new mem table in memory to serve the current write request. So it works in a similar way, except that instead of hash table, we are using a mem table to maintain the current set of writes. So you always arrange the current set of keys, and once it hits a certain size, you just move. So you will also have a similar segments here, segment 1, segment 2, as and when the writes are happening. And each of this will have, let's say, in this case, 10 is a key, and you may have value of Naga or whatever, and you may have another like 15, and again some other value. And similarly, like you will have 20, some other value. Let's say this also has like 15 and some value, and this 20 some value. So this is how these things are happening. But to be able to read, like we cannot, though it's in sorted order, since it's once it goes to the disk, like to be able to read, we need some kind of still some index, but we need not have index for all the keys, just like the previous hash indexes version. So here, as long as we are able to maintain the index for few keys, like let's say I'll just say that in the segment 1, I'll just have 2 keys. One maybe I'll just store to 10, and one maybe I'll just store to 20, like if I have many more here. If I want to query, so this is one index. So if we want to query for 15, then I see like 10 and 20 here. So it must be between these two. So I'll just go to 10 and I continue looking in that segment and see where I find 15, and then I can return that value. So this index is partial here. So we don't need to maintain the index for all the entries in all the segments. As long as you keep some partial pointers, like maybe you can just set some certain size, right? Like if for the keys of 10 or 20 ranges, or like since like the disks are normally very good in like up to 1 KB or 4 KB if you want to read sequentially, they can read it pretty quickly. If there are like 100 keys which can fit 100 keys which can actually fit in this 4 KB, so then we can actually use like the indexing to whichever number of keys can actually fit in that space. Then for those many number of keys, like we can just have one in our index. So that's one of the thinking pattern in deciding these partial indexes, depending on the disks that you choose and the kind of storage you have. Any questions? I'm speaking many
Partial indexing is also a type of hash table implementation, no?
Which one?
Partial indexing is also kind of hash table implementation. So we are having references to some partial.
Yeah, correct. Yeah, correct. Because though it's in sorted order, if each segment contains like 100,000 records, you still end up spending a lot of time scanning, right? So maybe you can use you can use binary search here only if all the values are of same size. If all the keys and values are of same size, then you can actually calculate where this record can actually be stored. But we cannot use binary search if the values are of different sizes, right? So that's why normally these indexes are used. So it normally contains some, like for every 100 records or 50 records, it can have one index pointer pointing to some of the record. And if some query comes, then we look up on this index and see where we are actually where we want to find that record.
So whenever a new segment goes into the disk, we have to again put the keys into the hash table. What's the partial index there is?
Yeah, we need to have this index built to support the reads, right? Like we need to be able to load this index into in memory for all the reads. So the idea is that like we may have the same keys in segment 1, segment 2, just like the previous scenario, and you may have the same keys in multiple, because it's possible that the writes are happening to the same keys again and again. So you may have the same keys coming up again and again, but they all will be sorted order in all the segments. So here also we will have that scenario of merging and compaction in the background. But as you know, like compared to the previous, how the merging looks like here, if the keys are sorted. You know the merge step of merge sort algorithm, right? So it's like if the keys are in sorted order, we just look the first two keys and compare like so that this merge can be done quickly and efficiently, because you know whether the key is present in others or not, like quickly. So you just like scan through two sorted orders and bring one new sorted index, something like that.
Could you explain again if we have duplicate record, one in segment 1 and one in segment 3, and how does that hash table find it?
So whenever this, if I'm running a merge step or compaction step on these two segments,
Before merging.
Before merging?
Before merging.
Oh, okay. Yeah. So this index is only for one segment. So it's not for all the segments. So this index is built for each segment. So index 1 for this one, then there will be separate index for this. Yeah, thanks for asking that. So there will be index 3 for this. When the merging happens, then this indexes, partial index also can be merged depending on the new set of entries in the segment. So we'll have an index for each of the segments. But just to note that this index won't take space like the hash indexes because it's partial and it only stores like few of them.
So even before merging, if we search for it, we still need to search for all the segment in all the segment.
Before merging, if you want to search in all the segments, is that the question?
Yeah. Let's say I have one record, record 1 in segment 1 and also record 1 in segment 3. So now the user search for record 1.
So we know that like this segment, like if we take this as a old one, this is the next one, like after this old, this is the next one which came. And this is the latest if we imagine. So that same concept still applies. If I see a 15 key here, and if I see 15 here and here, I know that this 15 segment key value is the latest one. Okay. So I just ignore the previous 2 segment values. But only thing is that this is in sorted order. I'm able to look up faster using this partial index. Someone is speaking very low. Can you speak louder?
Yeah, is it better now?
Yeah, now it's better.
Yeah, can you explain the partial index part again? So what would be the key there? So I understand the value would be the index segment. What would be the key for the partial index?
It's the same key which we are actually using. So I said like we'll have one, this is the index for this, and this is the index for this, and this is the index for this. So the key will be the same key that we use in the segment. Whatever the key that we are using in to sort, it's actually the sort key.
There would be multiple keys, right? So like if there are the values that you took for an example, 10, 15, 35, right? So we will have all the values as key?
No. These values I haven't written. It can be any objects or like a person record. This can be like an employee ID, and this can be like the employee record. And where in the keys I only store the employee ID like 10, and I'll say it's starting in offset. If it is 0 in the location, offset 0, or like if this is 100, I'll just specify the offset 100. And I won't specify the next record like 15 or 12 or something. Then I'll just specify somewhere 20 as the next index. And I'll actually point to 20th record. I won't have pointers for all the segment entries in this index. So this partial index. So this index will only have few entries in the sorted order. Like if I have 100,000 records like this, it may only have like 1,000 entries in the partial index. So if I'm finding some key which is not there in the index, then I know that like if the key is like in this case 15, and I only have the pointers for 10 and 20, then I know for sure that if I go to the 10, I can sequentially find out somewhere down the line the 15 record will like be existing.
Yeah, makes sense. That helps. Thank you.
So for any questions? Okay.
No, I'm good. Thank you.
Okay. So that's the idea of this. Like whenever you are writing the red black tree or like this mem table, which we call. So whenever it reaches certain size, we just try to flush the mem table to disk. When writing to disk, we pick some keys as our index, and we also store that index for faster lookups later.
I have a question. So when we search in the disk, we do linear search, right? Like it have a pointer to
yeah, correct.
zero,
So
and from there.
Yeah, correct. It will be linear, and yeah, so it will be linear search.
But how do we know the boundary of the record? Are we searching byte, each byte? How we know, like, we can jump from record 1 to record 2 and record 3? Or we just like
we have the format of the record and end marker, right? Like something which indicates the end of the record. Maybe like if you take the new line as record end, then we take that new line. Or if you are using some EOF kind of thing, or end of the file, I don't know. I don't think that's the correct one, but like it will be something like new line character or something. Because otherwise you need to distinguish between two records, right? Like in your storage, let's treat this like as a, if we treat this as a like a file, then like we can just say like we have the key and the value sequentially at some point, and then there is a end marker for this entry. Since we are talking about key value data now, sorry. So whenever this value ends, we need to have some marker to indicate the its end of this value entry. So that's how I think the lookups are done.
That means we will search for every byte, in the record, right? To see to look for the record.
Yeah, I don't think it will be like this. Maybe we'll have how much each record size is. Maybe somehow either in the index or like in the file. Maybe when writing this key value data, we just write like how many bytes this can be skipped. Like,
yeah.
So it won't be like the two, like as I explained, there will be some information about how much data of that key value space takes. So it can quickly jump onto that next record.
Yeah, maybe each record may have some sort of a header.
Yes.
But you have a specific format already, right? I mean, it's a key value pair. You decide the format how you store, so you can jump from one to another.
Yeah, when you are storing, like, since this is in the disk and it's in the form of bytes, like we just need some kind of, if it's in memory, we know like it's already clearly distinguished like key value. But when you come to file system, it's in terms of bytes, and you need to be able to find like some, like when the program is looking those passing those bytes, you need to know how many bytes to skip to the next record. So I think there will be some sizing ahead as a marker, which indicates how many bytes this key value might take.
Yeah, I see. That's the reason we cannot do binary search in the disk. Right? Because
yes, correct. Yeah. And we still can do the binary search if all the keys tend to take the same size, all the keys and value. Like if we know for sure that all the value takes only 100 bytes, then probably we can just calculate. If I'm looking for, I don't know, maybe you can just try to use some modified version of binary search to be able to jump quickly to some level, some mid. If we see that this key is greater than, then you can go back to the previous 100 bytes. So since we cannot guarantee this key in the key value system, the values and keys to be of same size, that's how I mean, like we cannot use binary search here, and we have this partial index. And the reading sequentially disks are still faster. It's only to get to that disk position, the magnetic disks needs to spin and seek to that position. Then if you are reading something sequentially, they'll be quicker. But only to seek to that sector or that block, it takes time. But once it is at certain position, they're faster in reading the data. Mm, so I hope that clears. So if there are no other questions, I'll get on to the other things here. Okay. So one of the challenges that we could actually face here, that like when you're suppose like you have this current mem table here, which is accepting the writes, and suddenly your machine crashes. So that data will in the mem table will be lost before writing to disk, right? So to overcome this, it actually uses a similar write-ahead log concept. Here it doesn't this WA log, write-ahead log. It actually just stores the keys in append-only order. So I can just store first 50 and then 30 and then like 60. So they are not in order, just like in the red-black tree. So as and when an insert is happening into the red-black tree, and there will be also write to a write-ahead log. So this is similar to like just append only. It keeps appending, but they are not in any sorted order, just like in red-black tree. So these are just for durability. So in the event something crashes, then we can recover the red-black tree or the mem table from this write-ahead log. So we can reconstruct this mem table from this write-ahead log, so that we don't lose any keys or values that we are writing to the database. So whenever we flush this mem table to disk, after we insert, then we can discard this. So then we initiate a new mem table, and we keep maintaining a new set of write-ahead log for that current mem table. So that's how this works actually to ensure durability.
So this is just before writing to disk. If the RAM crash, we should be able to recover.
Yeah, we should be able to recover the mem table, that is the red-black tree which maintains, like it reconstructs from this write-ahead log.
It's just a series of events, write, update, or something like that, right?
Yes. So first, actually, whenever some write is happening, the current mem table, it first writes to this write-ahead log, then adds entry into this mem table. And when we add an entry to the mem table, we know like where to insert, right? And we also rebalance as per our red-black tree or mem table rules. Only when it hits certain size, then we try to push to disk from the memory, and that's where we discard this whatever the entries in write-ahead log, and we'll construct a new mem table, which will again accept the writes in write-ahead log and also parallelly construct in memory.
Yeah.
Hey Naga, one more question. So let's say we are having 2 to 3 segments, whatever there are. So in both the segments, we are having some duplicate entries. So let's say in one segment, 15 is there in as the first key in the second segment. And in the third segment, again 15 is there as the first key. So both of their partial indexes will point to the 15.
No, there's a partial index for each segment. So so every record won't point to 15, right? Like there are some only few keys in the segment will be available in the partial index. But based on the value of 10 and 20 in the partial index, you know that if I go to 10 in the partial index, that location, if I sequentially scan through, I'll be able to find the 15 key. So similarly, there will be some 10, 20 here, like there may be some other records, or like in this segment, I may, since the 15 is the first record, I may even have the 15 directly pointing to 15. So here also I'll have 15 maybe directly pointing if that is the first record, and maybe the next index is 30 because, and I'll ignore all the in-between records.
Now, how will you get to know which of the 15 is recent?
Um,
Is
yeah,
that
I mean,
going
like
to
this.
happen from partial indexing side?
Since this is the latest segment, you just see where the 15 is, and 15 value is in this segment. You just ignore the previous segments. I haven't shown the merging part yet, but when you merge these two segments, so since 15, 20, 30 are already here in this, so you can just ignore the segment entries.
Okay, we should always start search from the recent segment.
Yeah, recent one. So if segment 3 is a recent, we always look into the recent segment. If the key is found here, you just return the value directly from here. And if you have merged, like as a result of this two segment merging, you will have another segment with both of the keys in sorted order. Again, this partial order, partial index will be combined to that new segment, so, such that those record pointers are again re-established. So when the merging happens, you also need to build a new partial index matching to that merge segment.
Okay. Thank you.
Mm-hmm. So here also, like to make the writes faster, we will use the mem table. Like it's like an in-memory writes, which are very faster. And as and when you push to disk, you'll maintain partial indexes. Like you'll create to some records in your segment. And when the merging hop happens, these partial indexes are also rebuilt and stored in the index. Stored in the disk. So whenever you want to read something from those segments, you load the partial indexes into memory and try to find where your records are there in the disk. So this is SS. Sorry, someone was asking.
No, I was giving up. Yeah, actually.
Okay. So that's about like constructing and maintaining. The fact that they use this log, write ahead log for durability, and which is again log structure. And these are also, these segments are also built like from recent and before recent, right? Like they're also in sequential order. So this also falls under log structured. That's why it's also called as LSM tree. So if this tree was on its own without this, then it's not like it's just a simple tree. But since it's using write ahead log along with this and following this concept, it's called as log structured merge tree. It's log structured, and since we are merging like in the process, so this is the same concept behind all the key databases. I already told, right? Like LevelDB is one storage engine which uses this, and RocksDB is an extension of this. So it extends from this, and it does something more. I don't know. And I think these two are the main, and Cassandra also uses this storage engine on the database perspective. And I think Bigtable also uses this LSM concept. Bigtable, Cassandra, and React also uses this. These two are like the storage engines. And sorry, this is also a database which uses this LevelDB storage engine. And this is a database we know. This is a database we know, which internally uses these concepts of log structure. LSM trees concept. Any questions? Okay, let me see if I missed anything. Yeah, and there are like some strategies which different databases used for this compaction purpose. So Some of them, when they are compacting this, the previous segments, some of them will make sure that each segment, when they are merging, they keep on increasing the size to make a larger segment. Those type of ones are called, that type of compaction is called like size tired compaction. Like till certain size, the segments are met, they keep on merging the recent segments to that big file, making as one large segment. And some also use like some leveling, like they try to merge two segments and few other segments. They keep maintaining certain leveled compaction. And I think you can actually go and read something more if you are interested. It's just a mechanism of how different databases that they use this concept. They use different mechanisms to merge and compact. So one is called level compaction, other one is like size tired. So each one has its own advantages and disadvantages.
When it merge, it will create a new file. Is that right?
When they merge, yes, they have to create a new merge segment. So if these two are in some place of the disk already, and there is a process which is merging, reading these two and merging, it will probably write a new segment in a new part of the disk with all the keys and values. So this will be the new segment in another portion of the disk. Once this is completely written and the new index is built, it just deletes this too. It just ignores this. So you have the free space already taken care. And it is key that if you are using leveled compaction, you mostly get this segment stored sequentially in the disk. If you are storing sequentially in disk, looking up, it's again easy, right? So if you use size tired, it's hard to find disk spaces which fit like large segment size continuously. Hard to find that memory, right? So that's some of the comparisons between these two type of merging. Am I clear?
Yes.
Okay. So yeah, if there are no questions, and we can move on to B trees, which follow a different concept. Please just scan through, make sure I didn't miss anything. Okay, yeah, I think I go. So now we will look into B trees. So the previous ones that we looked like hash indexes, SSTables, or LSM trees are actually the log structured storage engines, data structures which do the log structured storage engine. And the B trees is actually the page oriented. So this page oriented is like it thinks to organize the data which fits effectively on the disk. So we know that the disks are normally organized like into, I don't know how to represent correctly disk, but there will be some multiple layers of storage in the disk. I don't know. And each of them levels can have some sectors divided like this. And And somewhere like in each of this sector, this we take this each of this as sector 1 or sector 2, and one of the sector we may divide some continuous space as one block. So this block will normally be of 512 KB size. I think nowadays, I think hard disks support even bigger size blocks, but this is one of the typical size blocks. So the B trees are think to index the data considering this disk format, the way the data is actually stored. And if it is a magnetic disk, there will be some spinner which actually points to somewhere, and there will be something rotating this. I don't know how to represent this, but it will keep rotating in this disk, and it will point to some sector. And if there is a position in block where it needs to read data, it just spins that disk and reads the content sequentially and then reads back. So the B trees normally organize the data and store the data in terms of blocks, just like the disk that does. So, and coming to the order, B trees also store the keys in sorted order. But the way it works is different from block storage. We'll just look into that. I will erase this now. Let's take the same example of some numbers, right? Let's say this is some disk. Like we have, let's say if we have some 100 records in this, some portion of disk I'm showing. Just imagine this is like one block or something. Some block in disk. So if we just think like this is 100, some value of some person data like person 1, 101, we just store something like this, 102, and you keep on having this data like 20, and then you may have like 180, and then you may have like 200. So let's treat this as like some sequential storage in disk. And what if you wanted to create a index out of this? Definitely, like if you create a index for all the entries, then it's as good as I mean, like the index that I'm talking about is still in disk, but ensures an efficient access to this disk. So let's say that we will have some partial index. We'll say like 100, let's point here, and 120, let's point here, and 180, let's point here. Let's take another 200, point here. There may be some further records, like let's take this is like up to 1000. So we can have a another level of index. So this index can actually look the entries of up to from 100 to 200 efficiently. Like we just have 4 pointers, and each of them point to certain set of records. So this is like one level of index. But like if you have another 200 to 1000, you also have. So similarly, you may need to maintain some another index. So which will actually say from 220 to something, and then like 250 to something. Similarly, you will also need to have at least like if each index can store the entries of up to 200 size, you may actually have 4 blocks of storage. If if I mean, like, if I want to efficiently distinguish this, let's take this. This is taking like 100 MB of data, the whole 1000 records. This first block, which is of 512 KB index, can look up the first 200 records or act as an index for the first 200 records. And the next index, next 512 KB block of B index can actually look into next 200 records. Similarly, we can have another two indexes tables here. Let's say like we have 4 into 5 to 1 KB. So it's like in total, it will be like 2 MB of data we are using to store the indexes. So this is just like one level of indexes. But if the data keeps on growing, we cannot fit the whole data into this. We cannot keep on growing this indexes, right? Like we need to have this first level index, but we should also be able to find another level of index to be able to point to this. Like let's say, let's keep another master index, say 100, point to this first block, and 200, point to this another block, another like let's say 500, point to this third one, like 800, point to this fourth one. So now that, like, if there is any entry that we want to look up, this is like the first level index. If we want to look up like 101, we know that like 100 is here and 200 it goes to a different block. It must be in this first level. We come here again. The 100 is pointing to another place and 120 is pointing to another. 101 is still must be somewhere here if we go through linearly. So we go to this offset in disk and we continuously scan and find the 101 key and then return. We are able to index 1,000 record database like in 100 of size 100 MB with just 2 levels of indices. So let's assume this takes like 512 KB and this takes some 2 MB. With just 2.5 MB, you are able to efficiently query the data of 100 MB data. So this multi-level index. So before the B3 actually uses this multi-way indexes concept. If you try to flip this, it appears in the form of tree, right? So each node is actually pointing to subset of records. And each index is again pointing to subset of records. And only leaves in the B tree, like this, can act as a individual nodes, that's record pointers. So they can be leaves in the B trees. So this multi-level index, which is ensuring the key is stored in sorted order, the root will actually be only one, maybe like this. This can be the root. So since this is a first level index, this will act as a root and it will have a range of keys. Each key will have a certain pointer, like where that can be found. Any questions? I'm trying to explain in the best way possible. Is the idea clear?
Yes, Naga.
Okay. So that's a high level idea of like the B trees. We will just have all the indexes, which are these indexes are again part of disk storage. This is not in memory disk. So these indexes are again organized in terms of blocks in disk. So if we take like a 512 KB block, so each index is again organized in terms of blocks. And one of the thing that we need to notice is there may be certain indexes where we are not using the full memory inside the block, but we store, but the full memory is allocated for this B tree index to be able to add new entries. So in this case, maybe if I just erase this B tree of root, I think if I flip this in this way, it makes better understanding. This is a 4 child, right? So it has 4 references. Every node has 4 references. So these two can be of multiple levels depending on the size. And each of this level can actually have up to like 500 pointers. So if you organize in terms of, I mean, like with the B tree level, we can have up to maximum. So with B trees, like I'll just give an example with 4 levels. If each level uses say 500 pointers, within 4 levels, we can store the data. I mean, like we can index the data of database size of 256 terabytes. So this is quite significant size. So with just 4 levels of data, we can just continue having a B tree. B tree can support the size of 56 terabytes. We know that like they're quite efficient and their time complexity is log n. So we'll just look into, I'll try to represent the B tree in our regular tree shape. So it gives more meaning.
It's something like 500 pointers for each of the node.
Yes, each index. Let me represent this again. So yeah, each B tree node can have up to like if it has up to 500 pointers, and you know that clearly, like in each node, though the 500 are present, they're all in sorted order. You can apply the binary search if you're looking up for certain value or key. Let me represent the same thing. Like, let's say this is 100, and this is like 200. This is like 400, 700. So let's say this 100, which is pointing up here, it can actually store the indexes for like say 20, and this like 40, and then 60, and then 80, and then this 200 can actually store like 200, 220, 70 or 290. So each of this can actually have a pointer to each of this, and each of this again, let's say it'll have the keys of up to. Okay, I think I need to make sure 1, 2, 3, 4. So all of the nodes will have 4 levels. So I'm just showing the 4 levels. So let's say like 5, 10, 15. I don't know if this is visible. So okay, 20. So each of this again will have like 4 entries. So we'll have the leaves at the end. The leaf records will be at end. And all of this will actually have sequentially, like, let's say this is like 50, this is 100, this is 200, this is 800. I'm not able to represent correctly, but let's see. So each of this will actually keep on pointing to the childs, and if we take this, it maybe have like 65 and 70, 75, and this of them can be pointing to 70th record here, and this will actually point to the disk location of the data. So this is like multi-level, and each level will have up to like 4 pointers, or depending on the, I mean, like it can be up to 500 pointers, but you just try to, just to show an example, I just picked 4. And when you say 100, it'll have all the keys less than 100 and including. And this 200 will actually, yeah, I think I didn't mention it correctly, but this 200 will actually have the keys less than 200 and greater than 100. So there will be another tree here, and this is actually pointing to 400 left. So this will have up to 400, and the 700 left will actually have up to keys up to 700, and there will be another one which is greater than 700. This is like greater than 700. This is left hand pointer will be like less than 700. So this 400 left side, I mean like this pointer will actually point to all the keys less than 400. So all of this will be of multiple levels until it hits a leaf level. So this leaf level will actually contain a pointer to the actual data in place. I just tried to represent the same disk in like a tree fashion. So to make it look like a tree, maybe I think the previous one was better. So any questions?
This is like how it is organized.
Yeah, so this is how it's organized. Maybe you can go on further read B trees, and they are like very effective. And one of the strategies that I think B plus tree variation uses is it actually links all the leaf nodes in a doubly linked list fashion.
Okay.
So it will have like previous and next pointers. So suppose when you hit some to some leaf node and figured out that you need to move forward left or right, so that is also possible without going to the parent node and visiting back. So that is also one variation. So they're almost same as like B trees, but the leaves are actually will have the actual data. They will also have the previous and next pointers to make it efficient, like a linear scan. If you want to find here, if you want to find a range of keys, you just come to depending on where the key ranges are present. If you have to read all the data from 20 to 60, you just get all this child data, all this child data before 60, and then in the 60, what is the range that they have given. So I think this should be pointing this way. So you try to read all the subranges of this and then just return. So if you go to the disk, they all will be organized. Each block will be organized continuous sequence of keys. So they all will be in a linear fashion. So the disks are again good at reading the blocks continuously and return the data. So as you know, like the B trees are used in most SQL databases, and they're primarily used to, like if you are using the queries like in indexes, like if the query contains like where key, or like if you take like the age between like 10 and 50, something like that. So this is kind of range queries are efficient, like B trees are efficient to fulfill this kind of range queries. Even if you use like or whatever the things that you use in queries in the where condition, that's where mostly like this indexes will, if you have already indexed that data, if you're using B trees, like they are still efficient in retrieving the range queries. So since the B trees organize the data considering the disk format, disk block and things, so they are efficient in read. But if you are updating some records, like suppose this you have this 4 keys already, right? I'm inserting some key which was not already there, or if you have to insert something into this 4 level, since this is already full, now if I need to insert something, then you need to split. So 20, 40, like say less than 50 is split into separate B tree. So we can split this into like a 2 segments, like 2 of them will say 20, 40, and say this some keys are empty here in this, and another one. Sorry, I think I need to insert another parent here before this. So this will point to this, and this can point to here, and this can point to here, and maybe this will start at 60 and 80 and 90. So when you want to insert and you figured out that this node is full, you try to split the node into two, and you create another parent node linking to the parent. So when you split, you have to make sure that you create the new blocks of these nodes. You have to create the new nodes. When you're writing, this kind of scenarios will tend to happen. So if you are writing directly in one of the empty nodes where you have the space, you can directly insert without, suppose if you are inserting like 51, you may even come to some of the childs of this and try to figure out that like this is the place to insert. But the moment this pointers or the nodes get full, then you need to split them into two halves exactly. You don't split more than two, you just try to split into two, and you move 50% of the keys to one left and another 50% of the keys to the right, and you leave half of them empty. So this makes sure that the lookup is always in log n. So if you are splitting equally. So that's the reason, like if you have more pointers, then it's a large amount of data you can actually index. And since all of this are in like sorted order, you maintain in sorted order, you always can look up in log n inside each node, as well as in the leaves. Like when you get to the leaves, you can using binary search kind of like log n algorithm.
Mm-hmm.
So yeah, typically like as you can see with 4 levels, and if you use 500 pointers, you can index up to 256 terabytes of data. This is called like the branching factor. The number of references you have in each node will actually create like a branching factor, and how many levels you have, that many levels can define the size. And that I think there will be some formulas depending on the size of the data. You can actually try to look upon. Any questions?
When we update the record, so we update the record directly in this B tree?
If that record is already there, that key is there, all you need to find is where that record is there. Suppose if 200, you always come through the pointers where the 200 is, and you find the 200 record and try to update the record. So one of the drawbacks in write flow is, like suppose if your new record is taking more space than the previous one, then what you need to do, you need to readjust your blocks which are storing that records. You probably need to write a new block and point the reference to that if you don't, if your current storage can't fit. And there could be scenarios where in a sequential disk you leave fragments of spaces empty because you haven't filled the B tree, or like some records taken less space, and there is some other record which you are starting in the next block already. So in B trees, it is possible that the disk space is wasted if you are not, I mean, because there are chances that you don't have all the data to store in all part of the disk. And since you are splitting them in some particular sizes, some of the space will be wasted. But that's not the case in log structured storage. They're good in terms of utilizing the storage space, but they're not good for queries. But these are efficient for queries. But only thing is that the writes will take more time here, and they're a little complicated. As you can see, if something is full and you need to split, you tend to create two nodes and try to insert one more and try to point, right? Like if this is of 500 pointers, then it will be like some considerable task.
So when we delete record, a large record, do we have to right now? You know, we split them. Do we sometimes merge them back? I mean,
yeah, I think delete is little tricky. Yeah, I think if you keep on deleting the records and you don't suppose if you figure out that if you are deleting, maybe you deleted this, and this, and similarly you deleted this, and if you see two less than half, you can actually merge these two and make a single tree. So yeah, I think deleting is little tricky. So I think you can actually find out like how the deletion works in the B trees, but it takes I mean, like you try to make sure that it always works in log n time. If you have less than half of the keys in two of them, then it's good that you need to merge those ranges into one and create a common index.
I see. So unlike log, this one we don't need to merge the record, right?
We don't need to merge because all we are doing is we are creating another level of indices. If you find something is missing, so for example, if you keep on adding another extra range, if your parent is empty, you just add another one here, and in the child, like you again keep on adding the node levels, and the leaf node will actually have the data. All you make sure is that you have a reference to the from parent to the new, and if the parent also became full, you split this into two equal halves and insert one more master root index node, which will contain like this many levels. Am I clear?
Yes. Thank you, Naga.
So let me see if I missed anything in between. Yeah, so one of the scenarios, like when you're writing into B trees, suppose you're in the middle of writing some data and it got corrupted. Like suppose you are writing some data for some key, you are updating. In the process of updating that B tree, if the hard disk crashes or like some it's possible that this thing could the system crashes, then that wherever you are writing, it will be left halfway, right? So you'll end up having some corrupted nodes or leaf nodes. So to avoid those cases, even B trees use this write ahead log to make sure that any node that you are writing to B tree, you still write to write ahead log, and in the process of updating, if something goes wrong, then you visit this write ahead log. If something is there here, it means that the write is not completed, and you make sure that you go ahead and update that node again when you are back up and running. So even B trees use that write ahead log. So any question on that? And there is one more concept which B trees use, and it's possible, right? So suppose if somebody is, let's say, if in parallel, like if two of the threads, like in database, like there could be multiple transactions attempting to write to the same row or record, right? So let's say if two transactions attempt to write to the same leaf node, how B trees can effectively take up this is they can have a lock. I mean, like lock kind of thing controlled at each node. That like if something is being written, you can attach some small storage to each of those leaf nodes, right? To make sure that whether this is being written by some other transaction or not. So they can maintain locks at each of the leaves. So I mean, like that concept of logs is known as latches. They're like the logs on the leaf nodes, which make sure that any parallel or concurrent writes are not corrupting the record, and only one of them is actually writing.
Logs should be there only on the leaf node, no?
Yes,
Which
only
contains
on
the
the
data.
leaves. Yeah, only on the leaves. Yeah, that's all I think for B trees. I think some of the mechanisms when they're actually writing something or when they're splitting, what they try to do is they try to create a new copy of the current segment which is being, I mean, like current block which you are writing. They try to point to the new node. That kind of concept is also followed in some of the databases. Like every time there is a write on some of the nodes, instead of overwriting, they will always make sure that create a new block of data for that written record and update the pointer to point to the new block and discard the old one. So this ensures that the concurrency is met like quickly, like so there is no overhead of logs and other stuff if you are always updating, creating a new blocks of storage. I think some of them actually do that. Instead of overwriting, they always use a new location to write. I hope this at least gives some overview on B trees. And yeah, and as I said, like if you compare this B trees to LSM trees, like log structured ones, these are good in reading, and but like those are good for writing. So if your if your application is very write intensive, then you might lean towards log structured databases. And if you are more on like read intensive, then even B-trees are good at it. And some versions of LSM storage engines also are good because like they can also maintain the key ranges. But as long as they maintain the segments and internally the way the compaction is working and how they're doing that leveling, as long as they maintain, even they're considerably good for read. But overall, if you compare, like B-trees are efficient in terms of read.
Yeah, I think this is a good, I think good session on to see how the things are actually stored behind the scenes for any database. And
yeah, so we just need to keep in mind, like depending on the database we choose, what kind of storage engines they have capability with.
Yeah.
So if you just have these things like internally how the data is stored and how which storage engines they use, what structures, it makes us some good decisions, right? So,
yeah.
This is internal how database store data, right? But like, what about like when they create like, you know, like in SQL database, they create the index for the table, that would be different storage, is that?
I didn't, what was the question?
Like in SQL's table, right? The user can create many different indexes for each column. That would be different data structure than this one.
Yeah. I mean, like mostly, as long as you want to query them in some keys, like if you are creating some indexes which you are which uses B-trees, then they'll be able to query all this like between easily. I think the databases still use this for primary indexes. I think the B-trees to be able to find where they need to be able to query efficiently, right? So they definitely use B-trees. And for secondary indexes, and there are many types of indexes, right? Like we need to see there are some multiple composite indexes. and clustered, non-clustered, covered indexes. It might differ, but internally, definitely they have to use some concept of this B trees or some other modified concept for all these indexes that databases create.
Okay.
So yeah, definitely most of the SQL databases definitely use this. It's log structured in recent times after some of the papers from Google and other people, but B trees existed in from decades, from 70s or something. So most of the SQL databases would have started using B trees earlier to be able to serve queries efficiently. Okay, I'll stop recording and then maybe we can open up for questions.